What if I told you that right now, at this very moment, you are trapped in a cosmic prison? Not by walls or bars, but by something far more fundamental. Every thought you think, every movement you make, every atom in your body is being controlled by an invisible universal speed limit that you can never, ever break. And here's what will absolutely shatter your understanding of reality. This speed limit doesn't just control how fast things move. It controls time itself, space itself, and the very fabric of what you think is now. In 1905, a 26-year-old patent clerk named Albert Einstein was sitting in Bern, Switzerland, staring at the city's clock tower when he had a thought that would change human history forever. He imagined what would happen if he could ride a beam of light away from that clock. Would time stop? Would he see the clock's hands freeze? What he realized in that moment was so disturbing, so fundamentally wrong, according to everything humanity believed, that it took decades for the scientific community to fully accept it. Light doesn't just move fast. Light moves at the only speed that actually matters in our universe. And that speed, 299,792,458 meters per second, isn't just a number. It's the cosmic thread that weaves together everything you've ever known about reality. But here's where it gets truly mind-bending. The speed of light isn't really about light at all. Light just happens to be the messenger that revealed the universe's deepest secret. Causality itself has a speed limit. Every cause and effect in the entire universe is bound by this speed. When you flip a light switch, the light doesn't appear instantly. When the sun explodes in 4 billion years, we won't know about it for 8 minutes. When you look at the stars, you're not seeing the universe as it is. You're seeing the universe as it was, sometimes billions of years ago. You live in a universe where the past, present, and future are all happening simultaneously, just in different places, separated by this cosmic speed limit. And by the end of this exploration, you're going to understand why you can never, ever travel faster than light, not because of engineering limitations, but because of something far stranger. Physics itself will literally change the rules to stop you. Before we dive deeper into this rabbit hole, I need you to do something for me. If this is already breaking your brain in the best possible way, hit that like button right now. And subscribe, because we're about to go on a journey that will fundamentally change how you see reality. Also, drop a comment telling me where you're watching from and what time it is for you right now, because here's something wild. Depending on where you are in the universe, your now might be completely different from mine. We'll get to why that's true in a bit, but first, let me tell you about the cosmic speed limit that controls everything. Let's start with something that seems simple. Light travels fast, really fast. But just how fast are we talking? In 1 second, light travels 299,792,458 meters. That's about 7.5 times around Earth's equator in 1 second. To put that in perspective, if you could travel at the speed of light, you could go from New York to Tokyo in 0.06 seconds. You could reach the moon in 1.3 seconds. You could reach the sun in 8 minutes. You could cross the entire Milky Way galaxy in about 100,000 years. Now that last one might sound slow, but remember, the Milky Way is so incomprehensibly large that even at light speed, it takes 100,000 years to cross it. But here's what nobody tells you about the speed of light. It's not just fast, it's constant. No matter who measures it, no matter how fast they're moving, no matter what direction they're going, light always travels at exactly the same speed. Always? This is the part that broke physics. Think of it like this. Imagine you're on a train moving at 100 kilometers per hour, and you throw a ball forward at 50 kilometers per hour. To someone standing on the platform watching you, that ball is moving at 150 kilometers per hour, right? The speeds add up. That's common sense. That's how the universe should work. But light doesn't do that. If you're on a spaceship moving at half the speed of light, and you shine a flashlight forward, that light doesn't travel at 1.5 times the speed of light. It travels at exactly the speed of light. And here's the kicker. If someone standing still measures that same beam of light, they also measure it traveling at exactly the speed of light. The same exact speed. How is that possible? How can something be moving at the same speed relative to two different observers who are moving relative to each other? This is where Einstein comes in. In 1905, Einstein published his special theory of relativity, and buried in those equations was a revelation so profound that it would take humanity decades to fully grasp its implications. Einstein realized that the only way light could always travel at the same speed for everyone is if time and space themselves are flexible, not fixed, not absolute, flexible. When you move faster, time slows down for you. Space contracts for you. The universe literally warps itself to make sure that light always travels at the same speed for everyone. Let me say that again, because it's important. The universe warps time and space to protect the speed of light. It's not that light is special. It's that the speed of light represents something fundamental about the structure of space-time itself. It's the speed at which causality propagates through the universe. It's the speed at which information can travel. It's the maximum speed at which anything with mass can approach but never reach. And it's all because of one simple fact. Space-time is not what you think it is. Here's an analogy that might help. Think of space-time like a fabric, like a blanket stretched tight. When you're standing still on that blanket, time flows normally for you, and space is just space. But when you start moving really fast on that blanket, you start pulling on the fabric. The faster you move, the more you pull. And as you pull on the fabric of space, it compresses in front of you. Distances literally get shorter. But there's a cost. Time slows down for you to compensate. The universe is playing a cosmic balancing act, constantly adjusting space and time to make sure that light always travels at the same speed for everyone. Now, you might be thinking, okay, that's interesting, but how do we know this is true? How do we know time actually slows down when you move fast? Great question. Let me tell you about one of the most beautiful experiments in physics history, the muon experiment. Muons are tiny subatomic particles that are created when cosmic rays hit Earth's upper atmosphere, about 10 kilometers up. These muons are unstable and decay quickly, with a half-life of just 2.2 microseconds. At the speed they travel, about 98% the speed of light, they should only make it about 660 meters before half of them decay. That means almost none of them should reach Earth's surface. But here's the thing. We detect muons at Earth's surface all the time. Lots of them. How is that possible? The answer is time dilation. From our perspective on Earth, the muons are moving so fast that time slows down for them. Their 2.2 microsecond half-life gets stretched out, giving them plenty of time to reach the surface. But here's what makes this truly mind-bending. From the muon's perspective, time is flowing normally. Instead, it's the distance that shrinks. From the muon's point of view, Earth's atmosphere is only a few hundred meters thick, not 10 kilometers. The muon makes it to Earth's surface because space itself has contracted. Both perspectives are correct. That's the key insight. Time dilation and length contraction are two sides of the same coin. They're both manifestations of the fact that space-time's relative, not absolute. There is no universal now. There is no objective here. Everything depends on your frame of reference, your speed, your motion through space-time. And all of it, every single bit of it, is orchestrated to protect one fundamental constant, the speed of light. But wait, there's more. In 1971, physicist Joseph Haffel and astronomer Richard Keating took 4 cesium atomic clocks and flew them around the world on commercial airlines, twice, once eastward and once westward. When they got back and compared these traveling clocks to identical clocks that had stayed on the ground, they found something remarkable. The eastward traveling clocks had lost 59 nanoseconds. The westward traveling clocks had gained 273 nanoseconds. Time had literally run at different rates for the moving clocks compared to the stationary ones, exactly as Einstein's equations predicted. This isn't science fiction. This isn't theoretical. This is measured, verified reality. Time is not a constant flow that moves the same for everyone. Time is relative, flexible, and dependent on motion. And if you want even more proof, look at the GPS satellites orbiting Earth right now. These satellites are moving fast relative to us on the ground, which means time runs slower for them due to their motion. But they're also farther from Earth's gravity, which means time runs faster for them due to weaker gravitational time dilation. Engineers have to account for both effects, correcting the satellite clocks by about 38 microseconds per day. If they didn't make these relativistic corrections, GPS would be off by about 10 kilometers every single day. Your phone's navigation works because engineers understand that time is relative. Now let me blow your mind even further. Remember when I said light always travels at the same speed for everyone? That's true, but here's what's even weirder. From light's perspective, time doesn't pass at all. If you were a photon of light traveling from the sun to Earth, from your perspective, the journey would be instantaneous. Zero time would pass. You would be emitted from the sun and absorbed by your eyeball in the same instant. 8 minutes would pass for us, but for the photon, no time passes at all. In fact, from the photon's perspective, the entire universe in the direction of travel is compressed to zero thickness. The photon exists in a universe where space and time have collapsed completely. This is why nothing with mass can ever reach the speed of light. As you approach light speed, time slows down for you, approaching zero. Space contracts in the direction of motion, approaching zero. And here's the kicker. Your mass increases, approaching infinity. The closer you get to light speed, the more energy it takes to accelerate you further. To actually reach light speed would require infinite energy. The universe has literally built an infinite wall that says you cannot pass. Not because it's mean, but because the structure of space-time itself prevents it. Let me give you another analogy. Think of moving through space-time like moving through water. When you move slowly, the water barely resists. But as you move faster and faster, the water resistance increases. Eventually, you hit a point where the water is pushing back so hard that you can't go any faster, no matter how hard you try. Light speed is like that, except it's not water resistance. It's the fabric of reality itself pushing back. The universe will not let you break the cosmic speed limit. Now, here's where things get philosophical for a moment, and I want you to really sit with this. Everything you've ever experienced, every moment of your life, every interaction with another person, every sunrise you've watched, every star you've gazed at, all of it has been constrained by this cosmic speed limit. When you have a conversation with someone, you're not really having a real-time exchange. Sound travels at about 343 meters per second, which means there's a tiny delay between when someone speaks and when you hear them. That delay is almost imperceptible at normal distances, but it's there. The light carrying visual information about their moving lips travels faster, at light speed, but even that takes time. When someone standing 1 meter away speaks to you, the light from their face took 3.3 nanoseconds to reach your eyes. You're seeing them as they were 3.3 nanoseconds ago. Now scale that up. When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you look at the sun, you're seeing it as it was 8 minutes ago. When you look at the nearest star, Proxima Centauri, you're seeing it as it was 4.2 years ago. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. Your view of the universe is not a snapshot of now. It's a time machine showing you the universe at different moments in its history, all at once. The farther you look, the further back in time you see. And here's what's truly profound. There is no way to ever see the universe as it actually is right now. The concept of now doesn't even make sense on cosmic scales. When we say the Andromeda galaxy right now, what do we mean? Right now, according to whom? Right now, in what frame of reference? The answer is, there is no universal now. The present moment is not a universal slice of time cutting through the cosmos. It's relative, personal, and dependent on motion and gravity. If you're still with me, if your brain hasn't completely melted yet, take a second and leave a like on this video. We're about to go even deeper, and I promise you, what comes next will change everything you thought you understood about cause and effect. So we've established that light speed is the universal speed limit, and that this limit makes time and space relative. But why? Why does the universe have this speed limit at all? Why is it 299,792,458 meters per second, and not some other speed? And what's so special about light anyway? These are the questions that will take us to the next level of understanding. Here's the truth that most people don't realize. The speed of light has nothing to do with light. Light just happens to be the most convenient way to measure this speed. But what we're really talking about is the speed of causality. It's the speed at which cause and effect propagate through the universe. It's the speed at which information can travel. It's the speed at which any massless particle must travel. Light travels at this speed because photons, the particles of light, have no mass. Gravitons, the hypothetical particles that carry the gravitational force, also travel at light speed because they're massless. Anything without mass must travel at light speed. It's not a choice. It's a consequence of the structure of space-time. To understand why, we need to talk about something called space-time itself. In everyday experience, you think of space and time as separate things. Space is where things happen. Time is when things happen. But Einstein showed that this is wrong. Space and time are not separate. They're woven together into a single four-dimensional fabric called space-time. You don't move through space and then separately through time. You move through space-time along what's called a world line. Think of it like this. Imagine a sheet of graph paper where one axis is space and the other axis is time. Every object in the universe traces a path through this graph, moving forward in time and potentially moving through space. That path is the object's world line. Now here's the key insight. Everything in the universe moves through space-time at the same total speed. Always. You, me, a photon, a rocket ship, everything. We all move through space-time at the same speed. But wait, you're thinking, how can that be? I'm sitting still right now, and light is moving at 300,000 kilometers per second. How are we moving at the same speed through space-time? Here's the answer. When you sit still in space, you move through time at maximum speed. When you move through space, you have to borrow some of your motion through time to move through space instead. The faster you move through space, the slower you move through time. Light moves through space at maximum speed, which means it doesn't move through time at all. It moves through space-time at the maximum rate, but all of that motion is through space, none through time. This is why time stops for a photon. This is why light always travels at the same speed for everyone. And this is why you can never reach light speed if you have mass. If you have mass, you always have to maintain some motion through time. You can't allocate all your motion to space. You can get really close, borrowing more and more of your motion through time to move through space faster, but you can never reach 100%. The universe won't let you. Now let me tell you about one of the most brilliant scientists you've probably never heard of, Hermann Minkowski. In 1908, Minkowski, who had been one of Einstein's mathematics professors, reformulated Einstein's special relativity in terms of four-dimensional spacetime. He's the one who showed that space and time are unified. He gave a lecture where he famously said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Minkowski's spacetime, as it came to be called, is the geometric framework that allows us to understand relativity intuitively. In Minkowski's spacetime, the speed of light isn't just a speed limit. It's the slope of what's called the light cone. Imagine you're at a single point in spacetime. Everything that could possibly affect you in the future must be traveling toward you from the past at speeds slower than or equal to light speed. Everything you could possibly affect in the future must be things you can reach at speeds slower than or equal to light speed. These regions form a cone shape in spacetime, called your light cone. Everything inside your future light cone is potentially reachable. Everything outside it is absolutely unreachable, no matter what you do, no matter how advanced your technology gets. This has profound implications. There are events happening right now in distant galaxies that you will never, ever be able to influence. Not because you don't have a big enough rocket, but because the structure of space-time itself prevents any causal connection. The universe is partitioned into regions that are causally connected and regions that are causally disconnected, and the boundary between them is determined by the speed of light. Here's where it gets even stranger. Remember when I said there's no universal now? Let me show you exactly what that means. Imagine two events happening in the universe, event A and event B. If event A and event B are close enough together in space and time that light could travel from one to the other, then all observers will agree on which event happened first. Cause and effect are preserved. But if event A and event B are far enough apart in space and close enough in time that light couldn't travel from one to the other, then different observers moving at different speeds will disagree about which event happened first. For one observer moving in one direction, event A might happen before event B. For another observer moving in a different direction, event B might happen before event A, and for a third observer moving at yet another speed, events A and B might happen at exactly the same time. All three perspectives are equally valid. There is no objective truth about which event happened first. The order of causally disconnected events is relative. Let me make this concrete. Imagine someone on Earth sneezes at noon. Simultaneously, from Earth's reference frame, an alien on a planet 10 light-years away also sneezes. Now imagine a spaceship flying past Earth at 90% the speed of light. From the spaceship's perspective, due to the relativity of simultaneity, the alien sneezed hours before the person on Earth. But for another spaceship flying in the opposite direction at 90% light speed, the person on Earth sneezed hours before the alien. The order of events is not absolute. It's relative to your motion. This completely demolishes our everyday notion of now. There is no cosmic present moment that spans the entire universe. Your now and my now might include completely different sets of events, depending on our relative motion. The present is not a universal slice of time. It's a subjective, personal experience. Now I want to pause here and ask you something. How does this make you feel? Does it make you uncomfortable? Does it make the universe feel less real, less solid? Or does it make you feel a sense of wonder at how strange and beautiful reality actually is? Drop a comment and let me know, because this feeling, this cognitive dissonance, is the threshold you have to cross to really understand relativity. The universe is not obligated to make sense to your ape brain that evolved to throw rocks and avoid predators on the African savanna. The universe is under no obligation to match your intuitions, but it is consistent. It does follow rules. And those rules, once you understand them, reveal a reality far more interesting than the one you thought you lived in. Let's go deeper. We've talked about special relativity, which deals with objects moving at constant speeds. But what about acceleration? What about gravity? This is where Einstein's general relativity comes in, And this is where things get truly cosmic. In 1915, 10 years after publishing Special Relativity, Einstein published his general theory of relativity, and it was even more revolutionary than his first theory. General relativity makes a stunning claim. Gravity is not a force. Gravity is not something pulling you toward the Earth. Gravity is the curvature of space-time itself. Massive objects like Earth bend and warp the fabric of space-time, and objects moving through that warped space-time follow curved paths. You think you're sitting in a chair because Earth's gravity is pulling you down. But what's actually happening is that Earth's mass has curved space-time around it, and you're trying to move forward through time in a straight line. But that straight line through curved space-time makes you accelerate toward Earth's center. Think of it like this. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a dip in the sheet. Now roll a marble near the bowling ball. The marble will curve toward the bowling ball, not because the bowling ball is pulling it, but because the sheet itself is curved. The marble is following the straightest possible path through curved space. That's what gravity is. That's what you experience right now. You're sitting there following the straightest possible path through space-time, but because Earth has curved space-time around it, that straightest path keeps you pressed against your chair. And here's what's mind-blowing. This curvature doesn't just affect space, it affects time. The stronger the gravitational field, the slower time flows. This is called gravitational time dilation, and it's distinct from the time dilation caused by motion. Near a massive object, time runs slower than far from a massive object. This has been measured. In 1976, NASA launched a probe called Gravity Probe A that carried an atomic clock to an altitude of 10,000 kilometers. The clock at higher altitude, where Earth's gravity is weaker, ran faster than identical clocks on the ground by exactly the amount Einstein's equations predicted, about 4.5 parts in 10 billion. Your head is aging faster than your feet right now. The difference is tiny, impossibly small, but it's real. The top of a skyscraper is aging faster than the ground floor. Satellites in orbit are aging faster than us on Earth. Time is not uniform. Time is affected by gravity. The closer you are to a massive object, the slower time flows for you. Now combine this with what we know about motion. If you're in a strong gravitational field, time slows down. If you're moving fast, time slows down. Both effects are real, both are measurable, and both are consequences of the same underlying truth. Space-time is curved, flexible, and relative. And all of this curvature, all of this flexibility, is still constrained by the speed of light. Gravitational waves, ripples in space-time itself, created by accelerating masses, propagate at exactly the speed of light. When two black holes collide billions of light years away, the space-time ripples they create spread outward in all directions at light speed. And when those ripples pass through Earth, we can detect them with instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory. In fact, let me tell you about one of the most incredible scientific achievements in human history. On September 14, 2015, LIGO detected gravitational waves for the first time. The signal came from two black holes, each about 30 times the mass of our Sun, spiraling into each other 1.3 billion light years away. As they merged, they created ripples in space-time that spread outward at light speed, traveling for 1.3 billion years across the universe. When those ripples passed through Earth, they stretched and compressed space itself by less than 1,000th the diameter of a proton. And we detected it. Scientists Rainer Weiss, Barry Barish, and Kip Thorne won the Nobel Prize in 2017 for this discovery. This detection proved that space-time is a real physical thing that can ripple and wave. It proved that gravity travels at the speed of light. And it proved that Einstein was right about general relativity in ways that even he couldn't have imagined. Einstein himself thought gravitational waves would be too weak to ever detect. He was wrong about that, but he was right about the fundamental nature of space-time. Now here's something that will really bait your noodle. If gravity is the curvature of space-time, and gravitational waves propagate at light speed, what happens if you could somehow instantly move a massive object from one place to another? Would the gravitational field instantly update everywhere in the universe? No, it can't. Information can't travel faster than light. The gravitational field would update at light speed, propagating outward as gravitational waves. There would be a delay before distant parts of the universe knew that the object had moved. In fact, when you look at the sun, you see where it was 8 minutes ago. But you also feel its gravitational pull, as if it's pulling on you from where it was 8 minutes ago, not where it is now. The sun could disappear right now, and we wouldn't know for 8 minutes. We'd keep orbiting the ghost of where the sun used to be for 8 minutes until the information about its disappearance, traveling at light speed, both as the cessation of sunlight and as a gravitational wave, reached us. This is the tyranny of light speed. Information cannot travel faster than light. Causality cannot propagate faster than light. The universe has a built-in lag time, and that lag time increases with distance. The farther away you are from something, the more out of sync you are with it. On human scales, this doesn't matter. On cosmic scales, it means the universe is a patchwork of different nows, all slightly out of sync with each other, all causally disconnected by the finite speed of light. Take a moment and think about what this means for your life. Every person you interact with, you're interacting with their past self, not their present self. The delay is tiny, measured in nanoseconds for people in the same room, but it's real. You've never actually interacted with another person in real time. You've only ever interacted with where they were, who they were, what they were doing, a tiny fraction of a second ago. True simultaneity, true now across different locations, doesn't exist. If this is hitting you hard, good. That means you're really understanding it. Leave a like on this video if your mind is sufficiently blown, and let me know in the comments. Has this changed how you think about time? Because we're not done yet. We're about to explore what happens when you try to cheat the system, and why the universe always wins. So we've established that nothing can move faster than light, but humans are clever. We've spent the last century trying to find loopholes. What if we could bend the rules? What if we could find a way to travel faster than light without actually moving faster than light? Let me tell you about some of the most creative attempts to cheat the cosmic speed limit, and why they all ultimately fail, at least with our current understanding of physics. First, let's talk about wormholes. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical tunnel through space-time that connects two distant points. Imagine you could fold space-time like a sheet of paper, bring two distant points close together, and punch a hole through. You'd have a shortcut. You could step into one end of the wormhole and instantly emerge light years away at the other end. You wouldn't be traveling faster than light through space. You'd be taking a shortcut through space-time itself. Now, here's the thing. Wormholes are mathematically possible in general relativity. The equations allow for them. But, and this is a huge but, every solution we've found requires something called exotic matter, matter with negative energy density. And we've never found any exotic matter. We don't know if it exists. We don't know if it can exist. Most physicists think it probably can't exist, at least not in the quantities needed to hold a wormhole open. Even if you could create a wormhole, it would instantly collapse unless you could thread it with exotic matter to keep it open. But let's say, just for fun, that you could create and stabilize a wormhole. What happens then? Well, here's where causality rears its head. Stephen Hawking, one of the greatest physicists of the 20th century, proposed something called the chronology protection conjecture. The idea is that the laws of physics prevent time travel, and by extension, they prevent certain kinds of wormholes. Here's why. If you could create a wormhole and move one end of it while keeping the other end stationary, you'd create a time machine. Due to time dilation, the moving end would age slower than the stationary end. Now you have two ends of a wormhole that exist at different times. If you go through the wormhole in one direction, you go back in time. And if you go back in time, you could violate causality. You could kill your grandfather before your father was born. You could create paradoxes. Hawking's conjecture, which most physicists agree with, is that whenever you try to create a time machine, something in the universe will stop you. Maybe the wormhole will collapse. Maybe quantum fluctuations will destroy it. Maybe the laws of physics that we don't fully understand yet will intervene. But somehow, someway, causality will be protected. The universe will not allow you to break cause and effect. Okay, so wormholes are probably out. What about something else? What about the Alcubierre drive? This is a concept proposed in 1994 by physicist Miguel Alcubierre. The idea is beautiful in its cleverness. You don't move faster than light. Instead, you create a bubble of spacetime around your ship. You contract spacetime in front of your ship and expand spacetime behind it. The bubble, with your ship inside, surfs through space like a surfer on a wave. From the perspective of anyone inside the bubble, you're not moving at all. You're stationary inside the bubble. But the bubble itself is moving, and it can move faster than light because it's not an object. It's space-time itself moving. Brilliant, right? And again, mathematically allowed by general relativity. But, and you knew there was a but coming, the Alcubierre drive also requires exotic matter with negative energy density. Lots of it, more than probably exists in the entire observable universe. It also has some other nasty problems. For one, you can't steer it. The people inside the bubble are causally disconnected from the front of the bubble because of the space-time expansion. They can't send signals faster than light to the front of the bubble to control it. For another, when you turn the drive off, all the energy that accumulated at the front of the bubble during your journey gets released, potentially destroying everything in front of you. It's like arriving at your destination with a death ray. But even if we could solve these engineering problems, even if we could find or create exotic matter, there's a deeper issue. Both wormholes and warp drives require the ability to manipulate space-time on a massive scale. They require technology and energy levels that might be fundamentally impossible. The universe might simply not allow it. We don't know. We're still learning the rules. What about quantum entanglement? You've probably heard about this. When two particles are entangled, measuring one particle instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and hated it. It seemed to violate his cosmic speed limit. But here's the thing. Quantum entanglement cannot be used to transmit information faster than light. When you measure an entangled particle, you get a random result. You can't control what result you get. And the correlation with the other particle isn't revealed until you bring the measurement results together, which has to be done at light speed or slower. It's like this. Imagine you have two boxes, and you know one box has a red ball and one has a blue ball, but you don't know which is which. The balls are entangled in the sense that opening one box tells you what's in the other. If you open your box and see a red ball, you instantly know the other box has a blue ball, but you haven't sent information faster than light. The correlation was always there. You just revealed it. Quantum entanglement is like that, but weirder, because in quantum mechanics, the particles genuinely don't have definite properties until you measure them. But the point stands. No information actually travels faster than light. Every loophole we've found, every clever workaround, every attempt to cheat the cosmic speed limit either requires impossible physics or doesn't actually violate the speed limit when you look closely. The universe is remarkably good at protecting its most fundamental law. Causality has a speed limit, and that limit is the speed of light. Now, some of you might be thinking, okay, but what about tachyons? Tachyons are hypothetical particles that always move faster than light. If they exist, they would have some very strange properties. Their mass would be imaginary in the mathematical sense, meaning the square of their mass would be negative, and they would violate causality in weird ways, potentially allowing effects to precede their causes. Most physicists think tachyons don't exist. We've never detected one, and there are good theoretical reasons to think the universe doesn't allow them. But let's say, just for the sake of argument, that tachyons do exist. What happens then? Well, in a universe with tachyons, causality gets really weird. You could potentially send information backward in time. And once you can send information backward in time, you can create paradoxes. Most physicists interpret this as evidence that tachyons simply don't exist. The universe is chosen to be self-consistent, and that self-consistency requires that nothing moves faster than light. Here's what I want you to understand. The speed of light isn't just a speed limit on moving through space. It's a speed limit on causality itself. It's a limit on how fast information can propagate. It's a limit on how fast the future can depend on the past. Every attempt to violate this limit either requires physics we don't have and might not be possible, or doesn't actually violate the limit when you examine it carefully. The universe is telling us something fundamental. Cause and effect have a maximum speed, and that speed governs the structure of reality itself. And you know what? That's beautiful. It's frustrating for science fiction fans who want faster than light travel, sure. But it's beautiful because it means the universe is consistent. It means there are rules, deep mathematical rules, that can't be broken. And those rules, as strange as they seem, make the universe knowable, predictable, and ultimately comprehensible. If you're feeling the weight of this, if you're really grasping the implications, hit that subscribe button. We're about to transition from the physics of light speed to something even more personal. What this means for you, for humanity, and for our place in the cosmos. So let's talk about what the speed of light means for us, for our future, for our civilization. Because this cosmic speed limit isn't just an abstract physics concept. It has profound implications for humanity's long-term survival and our place in the universe. And honestly, some of these implications are heartbreaking, while others are strangely comforting. Let's start with the heartbreaking part. The universe is expanding. Not just expanding, but accelerating in its expansion. In 1998, two teams of astronomers, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, discovered that distant supernovae were farther away than they should be based on the age of the universe. This could only mean one thing. The expansion of the universe is accelerating. Something, which they called dark energy, is pushing the universe apart faster and faster. These three scientists won the Nobel Prize in Physics in 2011 for this discovery that changed everything we thought we knew about the universe's fate. Now here's where the speed of light creates a cosmic tragedy. Because the universe is expanding, and because that expansion is accelerating, there are galaxies that are moving away from us faster than light. Wait, you're thinking, didn't you just spend an hour telling me nothing can move faster than light? How can galaxies be moving away from us faster than light? Here's the thing. Those galaxies aren't moving through space faster than light. Space itself is expanding between us and them. Think of it like dots on a balloon. As you inflate the balloon, the dots move apart, but they're not moving across the balloon's surface. The surface itself is expanding. The dots on opposite sides of the balloon can be moving apart faster than light, not because they're traveling through the balloon's surface faster than light, but because the surface itself is stretching. This means there are galaxies we can see right now whose light reached us in the past that we will never, ever be able to reach. Even if we left today at 99.9999% the speed of light, we could never reach them because the space between us and them is expanding faster than we could ever travel across it. In fact, there are galaxies whose light is reaching us right now for the last time. After this moment, They'll accelerate beyond our cosmic horizon, and we'll never be able to see them again. Their light will be stretched by the expansion of space until it becomes undetectable. The observable universe, the bubble of space around us from which light has had time to reach us since the Big Bang, is about 93 billion light years across. But the truly reachable universe, the part we could ever physically travel to, even with unlimited time and perfect technology, is much, much smaller. And it's shrinking. Every second that passes, more of the universe becomes forever unreachable to us, because the space between us and those distant regions is expanding faster than light can cross it. In the far future, trillions of years from now, if any civilizations exist, they'll look up at the sky and see almost nothing. The expansion of space will have carried away all the other galaxies beyond their cosmic horizon. They'll think they live in a universe with only one galaxy, surrounded by infinite emptiness. They'll have no way to discover the Big Bang, because all the evidence will have been erased by cosmic expansion. They'll never know that their universe was once filled with hundreds of billions of galaxies. The speed of light, combined with cosmic expansion, will have hidden the truth from them forever. This is what the speed of light means for the long-term future. The universe is isolating us. The cosmic speed limit, combined with the expansion of space, means that humanity, or any intelligent civilization, is ultimately alone. We can see distant galaxies. We can study them. We can admire their beauty. But we can never reach most of them. We're trapped in a bubble of space called our local group, a collection of about 54 galaxies that are gravitationally bound together and won't be separated by cosmic expansion. Beyond that, unreachable, forever. Does that make you feel small? Isolated? Alone? It should. But here's the flip side, and this is where things get strangely beautiful. The speed of light also protects us. Because causality has a speed limit, because information takes time to propagate across space, the universe is partitioned into regions that can't affect each other. If something catastrophic happens in a distant galaxy, we're safe. If a civilization on the other side of the universe develops technology that could destroy the cosmos, they can't reach us. Not because they lack the technology, but because the structure of space-time itself prevents it. The speed of light creates a kind of cosmic immune system. Disasters, dangers, and threats are quarantined by distance and light speed delay. This gives evolution time to work. It gives civilizations time to develop independently. It prevents any single catastrophe from destroying everything all at once. The universe is not a fragile house of cards where one wrong move brings everything crashing down. It's robust, partitioned, and protected by the finite speed of causality. And here's something else to consider. The speed of light gives meaning to locality. Because information takes time to travel, where you are matters. Your local environment, your local interactions, your local relationships, these are what matter most. You can't instantly know what's happening on the other side of the universe. You can't instantly affect events light years away. Your sphere of influence is limited by the speed of light. And that's not a bug. That's a feature. It means your actions have local consequences. It means the people around you, the world you inhabit, the society you're part of, these are what you can actually affect. The cosmic speed limit forces you to focus on what's near, what's real, what's reachable. Think about it. In a universe without a light speed limit, everything would be connected to everything else instantly. Cause and effect would be infinitely entangled. There would be no locality, no independence, no separation between here and there. But because causality has a speed limit, because information takes time to propagate, the universe has structure. It has regions. It has neighborhoods. And that structure is what makes complexity possible. It's what makes life possible. It's what makes you possible. Let me paint you a picture of what your life looks like from the perspective of light speed. Right now, you're sitting wherever you are, watching or listening to this. Light from your screen or your environment is hitting your eyes at 299,792,458 meters per second. That light left its source nanoseconds ago and is just now reaching you. Your brain processes that information, which takes more time, about 100 milliseconds from perception to conscious awareness. So when you think you're experiencing now, you're actually experiencing a patchwork of events from different moments in the recent past, all stitched together by your brain into a coherent narrative of the present. But it gets weirder. Different parts of your brain process information at different speeds. Your visual cortex processes information faster than your prefrontal cortex. This means different parts of your brain are living in different moments in time, offset by milliseconds. Your consciousness, your sense of self, your experience of being a unified person existing in a single moment, that's an illusion created by your brain to make sense of the time-delayed, patchwork information it's receiving. You're not experiencing the present moment. You're experiencing a simulation of the present moment, constructed from the recent past and projected slightly into the future to compensate for processing delays. The speed of light and the processing speed of neurons, which is much, much slower than light speed, means that your subjective experience of reality is always slightly out of date. You live in the past. You always have. You always will. And so does everyone else. We're all stumbling through time, experiencing our own personal, slightly delayed versions of reality, and somehow we manage to coordinate with each other well enough to survive and thrive. Now zoom out. Think about humanity as a whole. We're a species spread across one planet, 12,742 kilometers in diameter. Light can circle the Earth 7.5 times in 1 second. That means, from the perspective of light speed, Earth is tiny. Humanity's entire civilization exists in a space that light can cross in a fraction of a second. We're all, in a very real sense, living in the same moment. When we talk about global events happening now, we're mostly right. The delays are negligible on human scales. But now think about becoming a spacefaring civilization. Imagine we colonize Mars. Mars is at its closest approach to Earth, about 55 million kilometers away. Light takes about 3 minutes to travel from Earth to Mars at closest approach, and up to 22 minutes when they're on opposite sides of the Sun. Now, imagine trying to have a conversation with someone on Mars. You say something. Your words travel at light speed to Mars, taking 3 to 22 minutes depending on orbital positions. They hear you, think about it, and respond. Their response takes another 3 to 22 minutes to get back to you. A simple back-and-forth conversation could take anywhere from 6 to 44 minutes. You can't have a real-time conversation. You can only exchange messages and wait. This changes everything about how interplanetary civilization would work. You can't have centralized real-time control. You can't have synchronous meetings. You can't coordinate instant responses. Every decision has to be made locally because waiting for instructions from Earth might take too long. The speed of light forces decentralization. It forces independence. It forces local autonomy. Now scale up to interstellar distances. The nearest star, Proxima Centauri, is 4.2 light-years away. If we sent a message today, it would arrive in 4.2 years. If they responded immediately, we'd get their response in 8.4 years. A single exchange would take nearly a decade, and that's the nearest star. Most stars are tens, hundreds, or thousands of light-years away. Any interstellar civilization would be fragmented by the speed of light. Each star system would be functionally independent, connected to others only by messages that take years or centuries to arrive. This is both terrifying and exciting. Terrifying because it means humanity, if we spread to the stars, will inevitably fragment. We'll become different cultures, different societies, possibly even different species, separated by distances so vast that communication becomes impractical. We'll never have a unified galactic government because the communication delays make centralized control impossible. Each colony will be on its own, making its own decisions, evolving in its own direction. Exciting because it means the experiment of human civilization will be replicated across the stars. We'll have thousands of different attempts, different approaches, different solutions to the problems of existence. Some will fail. Some will succeed in ways we can't imagine. And the light speed barrier will protect the successes from the failures. But here's the real question I want you to sit with. Knowing all this, knowing that the cosmic speed limit isolates us, that it separates us, that it makes the universe fundamentally lonely, does that make your life more meaningful or less? Does the fact that you live in a tiny bubble of space and time, causally disconnected from most of the universe, make your experiences less significant? Or does it make them more precious because they're local, immediate, and real? I'd argue it makes them more meaningful. In a universe where you can't affect everything, where your sphere of influence is limited by the speed of light, the things you can affect matter more. The people you can reach, the lives you can touch, the changes you can make in your local environment, these become precious. You can't save the whole universe. You can't even know what's happening in most of the universe right now. But you can affect what's near you. You can make a difference in your local pocket of space-time. And that difference will propagate outward at the speed of light, rippling through the cosmos, becoming part of the causal chain that shapes the future. Every action you take sends ripples through space-time. Those ripples are limited by light speed, sure, but they're real. They matter. They change things. And in a very real sense, you are made of the accumulated ripples from the past. The atoms in your body were forged in stars that died billions of years ago. The light from those dying stars carried information across the universe at light speed. Some of that information eventually became you. You are a pattern in space-time, sustained by the flow of energy and information from your environment, connected to the deep past by unbroken causal chains stretching back to the Big Bang, all mediated by the cosmic speed limit. The speed of light doesn't just limit how fast things can move. It defines how the past, present, and future are connected. It creates the structure of causality. And causality is what gives meaning to time, to change, to life itself. Without the speed limit, there would be no clear distinction between cause and effect. There would be no arrow of time. There would be no way to make sense of the universe. But with the speed limit, with the structure it creates, the universe becomes comprehensible. It becomes knowable. And that knowability is what allows beings like us to exist, to think, to understand, and to wonder. Let me bring this back to something concrete. Remember the GPS satellites I mentioned earlier? The ones where engineers have to correct for relativistic time dilation? Every time you use your phone to navigate, you're relying on corrections that account for the speed of light and the curvature of spacetime. General relativity isn't just abstract theory. It's in your pocket. It's helping you find the nearest coffee shop. The cosmic speed limit, the flexibility of time and space, these aren't just intellectual curiosities. They're practical realities that affect your daily life. And here's what's beautiful. You don't have to understand the equations to benefit from them. You don't have to be able to derive the Lorentz transformation or solve Einstein's field equations to use GPS. Universe follows its rules, whether you understand them or not. But when you do understand them, even a little bit, something magical happens. The universe becomes more amazing, not less. The fact that time and space are flexible, that causality has a speed limit, that you're living in a curved four-dimensional space-time, created by the mass and energy around you. This makes reality richer, deeper, and more beautiful than the naive understanding you started with. So let me ask you directly, has this journey changed how you see the world? When you go outside tonight and look up at the stars, will you see them differently? Will you remember that you're looking into the past, seeing ancient light that's been traveling for years or centuries or millennia to reach your eyes? Will you feel the weight of the cosmic speed limit, the isolation it creates, the structure it imposes? Will you feel connected to the deep time of the universe, knowing that you're made of star stuff, that you're a temporary pattern in the eternal flow of energy and information through space-time? If the answer is yes, then this hasn't been just a lecture. It's been a transformation. Leave a comment and tell me what you're feeling right now. Tell me if this has changed your perspective. Tell me if you see the universe differently. Because that's what education should do. It shouldn't just fill your head with facts. It should change how you see reality. And if you've made it this far, if you've stayed with me for over 90 minutes of deep physics and philosophy, you're part of a very select group. You're someone who cares about understanding reality at its deepest levels. You're someone who's willing to have their intuitions challenged, their assumptions questioned, their worldview expanded. That makes you special. That makes you part of the tiny fraction of humanity that looks up at the stars and asks, why and how and what does this mean? Don't forget to subscribe, because we're not done yet. We still have to talk about the edge cases, the extremes, the places where the cosmic speed limit creates the most mind-bending phenomena in the universe. We're going to talk about black holes, time travel, and the ultimate fate of the cosmos. And I promise you, the best mind blows are yet to come. Let's talk about black holes. Because if you want to see the speed of light doing absolutely bonkers things to space-time, there's no better place to look than at the most extreme objects in the universe. Black holes are what happen when gravity becomes so strong that not even light can escape. And that sentence, simple as it sounds, contains implications that will break your brain. First, let's understand what a black hole actually is. A black hole is a region of space-time where gravity is so intense that it has curved space-time to the point of breaking. At the center of every black hole is a singularity, a point where space-time curvature becomes infinite and our equations break down. Surrounding the singularity is the event horizon, a spherical boundary that marks the point of no return. Cross the event horizon, and you can never come back out. Not because you're not trying hard enough, but because all paths through space-time inside the event horizon lead to the singularity. The space-time curvature is so extreme that the direction away from the black hole literally doesn't exist anymore. All directions lead inward. Even light, traveling at the cosmic speed limit, can't escape. The photons are trying their hardest to get away, traveling at 299,792,458 meters per second. But space-time itself is dragging them back in. Think about what that means. Light is trying to escape, moving at the maximum possible speed through space-time, and it's still being pulled in. That's how warped space-time has become. The cosmic speed limit, which usually protects causality and prevents anything from being trapped, has been defeated by gravity. Or more accurately, gravity has warped space-time so severely that even moving at the cosmic speed limit isn't enough to climb out of the gravitational well. Now here's where time gets really weird. Remember how I said gravity causes time dilation? The stronger the gravity, the slower time flows. Well, near a black hole, this effect becomes extreme. If you were to watch someone fall into a black hole from a safe distance, you would never actually see them cross the event horizon. You'd see them falling slower and slower, their image getting redder and dimmer as the light climbing out of the gravitational well loses energy. From your perspective, they would appear to freeze at the event horizon, taking infinite time to cross it. The light from the moment they crossed the horizon would never reach you because it would be infinitely redshifted. But from the perspective of the person falling in, they'd cross the event horizon in a finite amount of time. They wouldn't notice anything special at the moment of crossing. The event horizon isn't a physical barrier. It's just a mathematical surface, marking the point of no return. From their perspective, they'd cross it, and then, depending on the size of the black hole, they'd have anywhere from microseconds to hours before they hit the singularity and were destroyed by tidal forces. This is the relativity of time taken to its most extreme. Two observers, one falling into a black hole and one watching from outside, experience radically different flows of time. The outside observer sees the falling person take infinite time to cross the horizon. The falling person crosses in finite time. Both perspectives are valid. Both are true from their respective reference frames. There is no objective answer to the question. Has the person crossed the event horizon yet? It depends on who's asking. But it gets stranger. Let's talk about rotating black holes. Most black holes in the universe are rotating because the stars that collapsed to form them were rotating, and the angular momentum has to go somewhere. A rotating black hole is described by the Kerr metric, named after physicist Roy Kerr, who derived the solution in 1963. Rotating black holes have some truly bizarre properties. First, they don't have just one event horizon. They have two. The outer one is the event horizon, the point of no return. But inside that is another boundary called the inner horizon, and inside that is a region called the ring singularity. Unlike a non-rotating black hole, where the singularity is a point, a rotating black hole's singularity is a ring. And here's the truly wild part. Mathematically, the equations suggest that you could pass through the ring's singularity and emerge into another region of spacetime. Maybe another universe, maybe another time. The equations allow for it. Now, before you get too excited, there are good reasons to think this isn't physically possible. The inner structure of a rotating black hole is unstable. Quantum effects that we don't fully understand probably destroy any pathway through the singularity. But the fact that the equations even allow for it shows you how strange spacetime becomes in these extreme conditions. The cosmic speed limit, combined with extreme spacetime curvature, creates regions where cause and effect, past and future, here and there, all get mixed up in ways that challenge our very notion of reality. Another bizarre feature of rotating black holes is something called frame dragging. The rotation of the black hole literally drags spacetime around with it. If you were near a rotating black hole, you would be pulled around in the direction of rotation, not by friction or any physical contact, but because spacetime itself is rotating. You could try to hover in place by firing your rockets, but you'd find yourself being dragged around anyway, because the space you're trying to stand still in is itself moving. This is the speed of light meeting rotation, meeting extreme gravity, and the result is that spacetime becomes like a whirlpool, swirling around the black hole. Close to a rotating black hole, there's a region called the ergosphere, outside the event horizon, where it's impossible to stand still. Spacetime is being dragged around so fast that even light beams trying to move against the rotation get carried along. You'd be forced to orbit the black hole, whether you wanted to or not, because staying still would require moving faster than light relative to the rotating spacetime, which is impossible. Now let's talk about what happens if you actually fell into a black hole. This is where things get personally terrifying. As you fall toward a black hole, the gravitational force on your feet, which are closer to the black hole, is stronger than the force on your head. This difference in gravitational force is called a tidal force, and near a black hole, it becomes extreme. You'd be stretched lengthwise and compressed sideways in a process that physicists call spaghettification. Yes, that's the actual technical term. You'd be stretched like spaghetti until you were ripped apart atom by atom. For a stellar mass black hole, a few times the mass of our sun, this would happen long before you reached the event horizon. You'd be dead, vaporized, torn to atoms. But for a supermassive black hole, millions or billions of times the mass of the sun, the event horizon is so far from the singularity that tidal forces at the horizon are actually quite weak. You could cross the event horizon intact, feeling nothing special. You'd have time to look around, to see the bizarre optical effects of extreme space-time curvature, before the tidal forces closer to the singularity eventually destroyed you. And what would you see? This is where the speed of light creates some of the most mind-bending visual effects imaginable. As you approach the event horizon, the light from the universe behind you would be blue-shifted, becoming brighter and shifted toward higher energies. Light from the direction of the black hole would be red-shifted and dimmed. As you cross the horizon, you'd see the entire future history of the outside universe play out in fast forward, compressed into a finite time by extreme time dilation. You'd see stars being born and dying, galaxies colliding, the universe aging billions of years in what seems like moments to you. And then, darkness. Once inside the event horizon, you'd look outward and see ... nothing. All the light is now traveling inward with you, toward the singularity. The only light you could see would be light falling in behind you. This is the cosmic speed limit taken to its breaking point. Light, the fastest thing in the universe, the carrier of causality, the thread that connects cause and effect, is powerless against extreme gravity. It's still traveling at light speed, still moving as fast as anything can possibly move through space-time. But the space-time itself is so warped that all roads lead to the singularity. And at the singularity, we don't know. Our equations break down. General relativity, which has served us so well everywhere else, fails at the singularity. Space-time curvature becomes infinite. Density becomes infinite. The laws of physics as we understand them stop making sense. This is where we need a theory of quantum gravity, a theory that unifies general relativity with quantum mechanics. We don't have that theory yet. String theory and loop quantum gravity are promising candidates, but we're not there yet. What we do know is that black holes aren't eternal. In 1974, Stephen Hawking made a stunning discovery. Black holes evaporate. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. The process is slow, incredibly slow for large black holes, but it's real. Over timescales of 1,067 years for a solar mass black hole, or 10,100 years for the supermassive black holes at the centers of galaxies, the black hole will evaporate completely, returning its mass to the universe as radiation. This evaporation process is mediated by the speed of light and the quantum properties of spacetime. Virtual particle pairs are constantly being created and destroyed everywhere in space due to quantum uncertainty. Usually, these pairs annihilate each other immediately. But right at the event horizon of a black hole, sometimes one particle falls in while the other escapes. The escaping particle becomes real radiation, carrying energy away from the black hole. To an outside observer, it looks like the black hole is glowing with thermal radiation. The black hole loses mass and eventually evaporates completely. This creates a profound puzzle called the black hole information paradox. When something falls into a black hole, all information about it seems to be lost. But quantum mechanics says information can't be destroyed. So what happens to the information when the black hole evaporates? Does it come back out in the Hawking radiation? Is it lost forever? Is there some new physics we don't understand? Hawking spent decades working on this problem, and in 2004, he finally conceded that information probably is preserved and encoded in the Hawking radiation in ways we don't fully understand yet. The speed of light is at the heart of this puzzle. Because causality propagates at light speed, because information has to travel at light speed or slower, the fate of information that falls into a black hole is intimately connected to how space-time behaves at the event horizon and how Hawking radiation carries information back out. We're still working on understanding this, and it's one of the deepest open questions in theoretical physics. Now I want you to think about what black holes mean for your understanding of reality. These objects exist. They're real. We've detected them through gravitational waves. We've photographed them using the Event Horizon Telescope, which captured images of the supermassive black holes at the centers of the M87 galaxy and our own Milky Way. These aren't science fiction. These aren't abstract mathematical curiosities. These are real physical objects in our universe, objects where space-time is so warped that cause and effect, past and future, light and darkness, all behave in ways that seem impossible but are absolutely real. The speed of light, that cosmic speed limit we've been talking about, meets its match in black holes. And yet, even in these most extreme conditions, the fundamental principles hold. Causality still propagates at light speed. Information still travels at light speed or slower, even if we don't fully understand how. The universe still follows rules, even in the most extreme conditions imaginable. And here's what's truly profound. We figured this out. Humans, apes who evolved on the African savanna to gather fruits and avoid predators, we developed mathematics sophisticated enough to predict black holes decades before we could observe them. Carl Schwarzschild derived the first black hole solution to Einstein's equations in 1916, just 1 year after Einstein published general relativity. And while Schwarzschild was serving on the Russian front in World War I, he sent his solution to Einstein from the trenches. Einstein was amazed. Schwarzschild died of disease just a few months later, never knowing that his solution would be vindicated, that black holes were real. We figured out that space-time could be warped to the breaking point. We figured out that gravity could trap light. We figured out all of this using nothing but mathematics, logic, and observations of how light behaves. That's the power of human reason. That's what makes us special. Not that we're the biggest or strongest or fastest, but that we can understand the universe at its most fundamental level. We can see past our intuitions, past our everyday experience, to grasp truths that seem impossible but are nonetheless real. Take a moment and let that sink in. You live in a universe with black holes, regions of space-time where the laws of physics, as you know them, break down, places where time stops, where space tears, where even light cannot escape, and you can understand them. You can grasp, at least conceptually, what they are and why they exist. That makes you part of a very special moment in cosmic history. The moment when the universe became conscious of itself, when the matter and energy that makes up reality organized itself in such a way that it could look back at the cosmos and understand its own origins, its own nature, its own fate. If that doesn't blow your mind, I don't know what will. Drop a like, hit subscribe, and let me know in the comments. How does it feel to live in a universe with black holes? Because we're about to take this to the final level, to the ultimate implications of the cosmic speed limit for the fate of everything. We've talked about how the speed of light controls motion, causality, time, space, and even the most extreme objects in the universe. But now I want to zoom all the way out and ask the biggest question of all. What does the cosmic speed limit mean for the ultimate fate of the universe? Where are we going? What's the end game? And what does that mean for you, personally, here and now? Let's start with what we know. The universe is 13.8 billion years old. We know this from multiple independent lines of evidence: the cosmic microwave background radiation, the abundances of light elements, the expansion rate of the universe, and the ages of the oldest stars. The universe began in the Big Bang, a moment when space-time itself came into existence. Not an explosion in space, but an explosion of space. Every point in the universe was once the same point. Space has been expanding ever since, carrying galaxies apart. And here's what changed everything. As I mentioned earlier, the expansion is accelerating. Dark energy, whatever it is, makes up about 68% of the universe's energy budget, and it's pushing space apart faster and faster. This has profound implications for the future. In the short term, nothing much changes. Our local group of galaxies, held together by gravity, will remain bound. In fact, in about 4.5 billion years, the Milky Way and Andromeda galaxies will collide and merge, forming a larger elliptical galaxy that astronomers have already named Milkometa. The Sun will become a red giant around the same time, eventually engulfing Earth and then shrinking to a white dwarf. But our local galaxy cluster? It'll be fine for trillions of years. However, the rest of the universe is a different story. Galaxies outside our local group are moving away from us, and they're accelerating. In about 100 billion years, every galaxy beyond our local group will have moved so far away that their light will be redshifted beyond detectability. Future astronomers in the Milkometa galaxy will look up at the sky and see almost nothing. Just the stars of their own galaxy, surrounded by darkness. They'll have no way to discover that the universe is expanding, because everything else will have disappeared beyond their cosmic horizon. This is the tyranny of light speed combined with cosmic acceleration. Information is being hidden from us, erased from the universe, not by being destroyed, but by being pushed beyond the point where light can ever reach us. The cosmic speed limit means there's a boundary to what we can ever know, ever see, ever reach. And that boundary is shrinking. But let's go even further into the future. In YA years, 100 trillion years, star formation will cease. All the gas and dust will have been used up or dispersed. The universe will enter the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. These objects will slowly cool, radiating away their heat into the ever-expanding void. In YY years, even protons might decay, turning all remaining matter into radiation. In 10,100 years, black holes will evaporate via Hawking radiation. And then, the heat death. The universe will reach maximum entropy, a state where no free energy is available to do work. The temperature will approach absolute zero. Space will still be expanding, but it'll be empty. No stars, no galaxies, no planets, no life. Just an infinite expanding void filled with faint radiation, getting fainter and more dilute forever. This is called the Big Freeze or heat death, and it's the most likely fate of our universe, given current understanding. The cosmic speed limit plays a crucial role in this fate, because energy and information cannot travel faster than light, because entropy must increase, because the second law of thermodynamics is enforced by the structure of space-time itself. The universe is doomed to eventually run down. All the complexity, all the beauty, all the life, it's temporary. A brief flicker in the infinite cold darkness of eternity. Now, how does that make you feel? Does it make you feel nihilistic? Does it make everything seem pointless? Does it rob your life of meaning to know that in the incomprehensibly distant future, everything will end in cold, dark emptiness? Or does it make every moment more precious? Does it make your life, your experiences, your relationships, your accomplishments more meaningful because they're temporary? Because they exist in defiance of entropy, in the brief window of cosmic history, where the universe is complex and interesting and capable of supporting consciousness? I'd argue for the latter. The heat death of the universe, trillions upon trillions of years in the future, doesn't diminish the meaning of your life now. If anything, it enhances it. You are alive in the stelliferous era, the age of stars, the brief cosmic moment when the universe is full of light and warmth and complexity. You are made of atoms forged in the nuclear furnaces of stars, brought together by billions of years of cosmic evolution, organized into a pattern capable of experiencing, understanding, and appreciating the universe. You are the universe becoming conscious of itself. You are how the cosmos knows its own structure, its own history, its own laws. Every time you learn something about physics, about space-time, about the speed of light, you are fulfilling the universe's potential for self-knowledge. And that's meaningful. That matters. Not in some cosmic eternal sense, but in the here and now, in this brief window of time when meaning is possible at all. The speed of light, the cosmic speed limit, is part of what makes you possible. Causality needs a speed limit to work. Complexity needs causality to build up. Life needs complexity to emerge. Consciousness needs life. Meaning needs consciousness. It's all connected, all intertwined, all mediated by the fundamental constants of nature, including the speed of light. And here's something beautiful. You are affecting the future. The light from every moment of your life is radiating outward into the cosmos at light speed. Every photon that bounces off your face carries information about you into the universe. That information is spreading outward in an expanding sphere, growing at 299,792,458 meters per second. Right now, information about you from 1 second ago has spread out to form a sphere about 600,000 kilometers in diameter. Information about you from 1 year ago is in a sphere about 9.5 trillion kilometers across, having reached the outer edges of the solar system. Information about you from when you were born is tens of light years out, having passed dozens of nearby stars. You are writing your story on the fabric of space-time itself, and that story is propagating outward at the cosmic speed limit, becoming part of the permanent structure of the universe. In a very real sense, you are immortalized in the light cone of your existence. Every moment of your life creates ripples in space-time that will propagate forward forever, becoming fainter but never truly disappearing, becoming part of the causal chain that shapes all future events. This isn't metaphor. This is physics. The light that bounces off you right now will travel through space forever unless it hits something. Some of those photons will escape Earth, escape the solar system, and travel through the cosmos for billions of years. Long after you're gone, long after Earth is gone, long after the sun has died, photons carrying information about this moment will still be traveling through space. You are literally made of light scattered through time. Now let me bring this all the way back to where we started and connect everything we've talked about. The speed of light, 299,792,458 meters per second, isn't just a number. It's the fundamental organizing principle of reality. It's the speed at which causality propagates. It's the exchange rate between space and time. It's the cosmic speed limit that nothing can exceed. It's the slope of the light cone that defines what's possible and what's not. It's the speed at which information travels. It's the velocity of massless particles. It's the ultimate speed limit enforced by the structure of space-time itself. Everything we've discussed flows from this one constant. Time dilation happens because the universe must preserve the speed of light for all observers. Length contraction happens because space and time trade off to keep light speed constant. E equals mc happens because mass is crystallized energy, and the conversion factor is the speed of light squared. Black holes happen because gravity can warp space-time so severely that even light cannot escape. The expansion of the universe creates cosmic horizons because regions of space can recede from each other faster than light can travel between them. The heat death of the universe is inevitable because entropy must increase and information cannot be destroyed or travel faster than light. Your existence, your consciousness, your ability to understand all of this happens because causality has a speed limit that allows complexity to build up through stable causal chains. One number, one constant, one cosmic speed limit, and from it flows the entire structure of reality as we know it. But here's what I really want you to understand, the core message that should change how you see everything. You are not separate from this. You're not an observer standing outside the universe looking in. You are part of the universe. You are made of the same space-time, governed by the same laws, subject to the same cosmic speed limit as everything else. When you move, time dilates for you, even if the effect is too small to measure. When you exist, you curve space-time around you, even if the curvature is infinitesimally small. You are part of the cosmic dance of matter and energy flowing through space-time at various speeds, all limited by the ultimate cosmic speed limit. And that means everything you do matters. Every choice you make sends ripples through space-time. Every word you speak, every action you take, every thought you think, it all becomes part of the causal structure of the universe, propagating forward at the speed of light or slower, affecting the future in ways you'll never fully know. You can't affect the distant past. The cosmic speed limit prevents backward causality. You can't instantly affect distant parts of the universe. The speed limit creates a delay. But you can affect your local environment, your light cone, the region of space-time that's causally connected to you. And that's enough. That has to be enough. Because that's all anyone can do. That's all anyone has ever done. Einstein couldn't change the past. He couldn't instantly reshape the universe. But he could affect his local environment, his light cone, by thinking deeply and writing down equations that changed how humanity understands reality. Those ideas propagated outward through space-time, first through conversations and letters, traveling at the speed of sound and the speed of mail delivery, then through books and papers, traveling at the speed of printing and distribution, then through the internet, traveling at the speed of light through fiber optic cables. And now those ideas are in your head, changing how you see reality, affecting what you'll do next, creating new ripples that will propagate into the future. This is how consciousness affects the universe. Not by violating the laws of physics, not by breaking the cosmic speed limit, but by working within the constraints, by using the structure of causality to reshape the future one local interaction at a time. You are a pattern in space-time that can self-replicate through ideas, through teaching, through influence. The pattern that is you, your knowledge, your values, your way of seeing the world, can be copied into other minds through communication. And those copies can propagate forward, affecting the future long after your physical body has returned to the dust of stars from which it came. Let me tell you one final story that brings this all together. In 1977, NASA launched two spacecraft, Voyager 1 and Voyager 2. These spacecraft visited Jupiter, Saturn, Uranus, and Neptune, sending back stunning images that changed our understanding of the outer solar system. But they didn't stop there. They kept going. Today, both Voyager spacecraft have left the solar system and entered interstellar space. They're still functioning, still sending back data, traveling at about 17 kilometers per second relative to the Sun. On board each Voyager spacecraft is a golden record, a time capsule containing sounds and images from Earth, music from different cultures, greetings in 55 languages, sounds of nature, wind, thunder, birds, whales, images of humans, our cities, our technology, our world. The records also contain encoded instructions showing aliens how to play the record and where Earth is located in the galaxy. Now here's the thing. The Voyager spacecraft are traveling at 0.006% the speed of light. At that speed, they'll reach the distance of the nearest stars in about 40,000 years. The golden records are expected to remain playable for billions of years, long after Earth is gone, long after the Sun has died, long after humanity has either spread to the stars or gone extinct. Those records are humanity's message to the cosmos, traveling outward at a tiny fraction of light speed, but traveling nonetheless. Think about what that means. Right now, at this very moment, those records are carrying information about humanity deeper into space. Every second, they get 17 kilometers farther from Earth. Every year, they travel over 500 million kilometers. Every century, 50 billion kilometers. They're slow by cosmic standards, but they're persistent. They're patient. And someday, in the incomprehensibly distant future, they might be found by another civilization. And that civilization will learn that once, on a small blue planet orbiting an ordinary yellow star, there lived a species that looked up at the cosmos and wondered if they were alone. A species that created art and music and science. A species that understood, at least a little bit, the universe they lived in. A species that left a message saying, "We were here. We existed. We mattered." The cosmic speed limit means that message will take an incredibly long time to reach anyone who might find it. But it also means the message is protected, preserved, propagated forward through time in the stable causal structure of space-time. The Voyager golden records are riding the light cone of Earth's existence outward into the cosmos, slower than light, but part of the same causal structure, part of the same cosmic information network that binds past, present, and future together. You are doing the same thing on a smaller scale. Every day of your life, you're creating records of your existence. Photons bouncing off you, sounds you make propagating through air, actions you take that affect other people and objects, memories you create in other minds, ideas you share that get passed on. You are leaving your mark on space-time, writing your story on the fabric of reality itself, and that story will propagate forward, becoming part of the permanent causal structure of the universe. The speed of light doesn't limit this. It defines it. It gives it structure. It makes it possible. Without the cosmic speed limit, without the stable causal chains it creates, none of this would be possible. There would be no way to preserve information, no way to connect past and future, no way for your existence to have meaning that extends beyond the immediate moment. So here's what I want you to take away from this entire journey. The speed of light is not a limitation. It's a liberation. It's what makes you possible. It's what makes meaning possible. It's what makes the universe comprehensible and beautiful and worth understanding. The cosmic speed limit is the universe's way of saying, causality matters. Cause and effect are real. The past shapes the future in predictable, knowable ways. You can understand this. You can work with this. You can make a difference within the constraints of physical law. And you are making a difference right now. By learning this, by understanding it, by letting it change how you see reality, you've become part of the grand project of cosmic self-understanding. You're part of the process by which the universe comes to know itself. And that knowledge, that understanding, will propagate forward through space-time, affecting the future in ways neither of us can predict. When you go outside tonight and look up at the stars, you'll see them differently now. You'll know that you're looking into the past. You'll know that the light from those stars has been traveling for years or centuries or millennia to reach your eyes. You'll know that you live in a curved four-dimensional space-time governed by Einstein's equations. You'll know that time is relative, space is flexible, and causality has a speed limit. You'll know that black holes exist where space-time tears itself apart. You'll know that the universe is expanding, accelerating, racing toward an eventual heat death trillions of years from now. You'll know that you are made of star stuff, organized by billions of years of evolution into a pattern capable of understanding all of this. And you'll know that you're not alone. You're part of a species that figured this out. You're connected to Einstein sitting in that patent office in Bern, imagining riding a beam of light. You're connected to Minkowski reformulating relativity in terms of space-time. You're connected to Schwarzschild deriving black hole solutions from the trenches of World War I. You're connected to Hawking discovering that black holes evaporate. You're connected to the engineers who launched Voyager and the scientists who detected gravitational waves and the astronomers who measured the acceleration of cosmic expansion. You're connected to all of humanity's grand project of understanding reality, all of it bound together by communication signals propagating at or below the speed of light. This is your heritage. This is your birthright as a conscious being in the universe. You get to know this. You get to understand this. You get to be part of this. And that understanding, that knowledge, will change you. It already has. You're not the same person who started watching or listening to this. You've been transformed by ideas, by understanding, by the realization that the universe is stranger and more beautiful than you ever imagined. So let me ask you one final time. What will you do with this knowledge? How will you let it change you? What ripples will you send into the future? What mark will you leave on space-time? Because you will leave a mark. You can't help but leave a mark. Every moment of your existence creates ripples that propagate forward at the speed of light or slower, becoming part of the permanent causal structure of the universe. Make those ripples count. Make them meaningful. Make them beautiful. Not for some cosmic audience, not for eternal glory, but for the here and now, for the brief window of time when you exist, when you can experience and understand and affect the world around you. The cosmic speed limit ensures that your influence will propagate forward, affecting the future in ways you'll never know. But it will propagate. It will matter. It will be part of the grand tapestry of cause and effect that is the universe. The light speed that rules the universe doesn't imprison you. It connects you to the past through the unbroken causal chains that created you, to the future through the ripples you send forward with every action, to the entire cosmos through the fundamental laws of physics that govern all matter and energy in space-time. You are not separate from the universe. You are an intrinsic part of it. You are how the universe knows itself. You are how space-time becomes conscious. You are how the cosmic speed limit, that abstract mathematical constant, becomes meaningful. And that, ultimately, is what the speed of light teaches us. Not just that causality has a speed limit, not just that space-time is curved and flexible, not just that time and space are relative, but that we are part of something vast and ancient and beautiful. We are patterns in space-time, temporary arrangements of matter and energy, governed by the same laws as stars and galaxies and black holes. And for this brief cosmic moment, we get to exist. We get to experience. We get to understand. We get to matter. The speed of light rules the universe. But understanding the speed of light frees your mind. It shows you that reality is not what it seems. It shows you that time and space are woven together into a single fabric. It shows you that you are connected to the cosmos in the most fundamental way possible. It shows you that every moment matters, every choice counts, every action sends ripples into the future. So make your choices carefully. Live your life fully. Understand the universe deeply. And remember that you are part of something larger than yourself, something beautiful and vast and governed by mathematical laws that we, against all odds, have managed to understand. Thank you for taking this journey with me. Thank you for staying curious, for asking questions, for wanting to understand reality at its deepest levels. If this has changed how you see the universe, if it's blown your mind even a little bit, please hit that like button and subscribe. Share this with someone who needs to have their mind expanded. Leave a comment telling me what you think, how you feel, what questions you still have. And remember, you live in a universe governed by the speed of light. A universe where time is relative, space is curved, and causality propagates at 299,792,458 meters per second. A universe more strange and beautiful than you ever imagined. And you get to be part of it. You get to understand it. You get to experience the cosmic wonder of existence itself. Make it count. Every moment is propagating forward at light speed, becoming part of the permanent structure of space-time. Your story is being written on the fabric of reality itself. What will it say? What ripples will you send into the future? The cosmic speed limit ensures those ripples will propagate forward forever, becoming part of the eternal causal structure of the universe. You are the universe understanding itself. Never forget that. Never take it for granted. And never stop wondering, questioning, and seeking to understand the cosmos that gave rise to you. The light speed rules the universe. But you, by understanding it, transcend its limitations. You become more than just matter flowing through space-time. You become consciousness, meaning, purpose. You become the universe's way of knowing its own deepest secrets. And that makes you, right here, right now, in this brief moment of cosmic history, absolutely extraordinary. Thank you for watching. Until next time, keep looking up, keep asking questions, and keep seeking to understand the beautiful, bizarre, mind-bending universe we call home.